Hi everyone, we are Adam, Ben, Zainab, and Uma from Part 1, and this is our task analysis for the Pelican Colonies modeling task. Think of this video as a short professional development resource. If you are a colleague considering this task for your K to 8 classroom, we want to share what we actually learned from working through it ourselves, both the individual Part A component and the group Part B component. We are going to cover three areas: the general task characteristics, the modeling competencies it elicits, and its socio-critical and sustainability dimensions. Here is how the video is organized. I will walk you through the general task characteristics, including what the real world problem is, how it connects to the curriculum, and whether it is relevant and motivating for students. Zainab will then take you through the modeling competencies, tracing the modeling cycle directly through our team's work on parts A and B, and Adam will close with the socio-critical and sustainability dimensions, including both what the task does well and where it falls short. We will finish with key takeaways you can bring back to your classroom. So let us start at the beginning. What is the real world problem this task is built around? The American white pelican was once a threatened species. Population numbers dropped because of human disturbance at nesting sites, habitat loss from changing water levels, and environmental contaminants that caused eggshell thinning. Since the 1960s, population have been slowly recovering, but only because breeding colonies are now actively protected. Here is the practical challenge. Pelicans are extremely sensitive to disturbance during nesting season. If a researcher walks into a breeding colony, the adult birds abandon their eggs. Those eggs can overheat in direct sunlight, get taken by predators like gulls and coyotes, and in severe cases, the adults may not return to the site at all. So the US Fish and Wildlife Service cannot simply send someone out to count nests on the ground. The act of counting would destroy what they are trying to protect. That is the context. Now, here is the task itself. For this task, we were placed in the role of a research team. We received a memo from a wildlife biologist named Elise Hart from the US Fish and Wildlife Service. Along with the memo, we received two aerial photographs of two different nesting colonies and two satellite site maps showing the full boundaries of each colony site. Our job was to develop a procedure for estimating the number of nests at each site, test that procedure, state our assumptions clearly, and recommend which colony should receive priority conservation protection. And this is worth saying clearly. This is not a textbook scenario dressed up to look applied. This is the actual methodology researchers use. We were working with the real tools of wildlife population monitoring. That authenticity matters for engagement and for genuine mathematical purpose. Now, is this task relevant and motivating for K to 8 students? I think it genuinely can be, but with one honest caveat. The task is set in a US federal agency context. For students in Alberta, that distance can reduce the that this matters to me feeling. The good news is that recontextualization is easy. Alberta has colonial waterbird nesting sites on lakes across the province under the same recreational and development pressures. One adaptation of the memo and the task becomes local and immediate. The motivational hook, once students understand it, is strong. Their mathematical estimate is not just a grade, it directly influences which habitat gets a conservation fence and which one does not. That kind of authentic purpose changes how students engage with the mathematics. On curriculum connections, the mathematics in this task maps directly to Alberta's K to 8 program of studies. Area and linear measurement are central outcomes in grades 4 through 6. Proportional reasoning is a major focus in grades 6 through 8. Scale and ratio appear in grades 7 and 8. The task also adapts well across levels. For younger students, you provide the photograph area already calculated and ask them only to count and scale up. For older students, you remove all scaffolding and have them design the full procedure themselves. And the core problem stays the same at every level. Before the group work in Part B, each of us completed Part A individually. And I want to spend a moment here because I think Part A is underestimated. The first question asks, what would you need to know to estimate the number of pelicans in a colony? That sounds simple. It is not. When I worked through it, I came up with 11 factors, including the total physical area of the colony, average nest density, the current stage of the breeding season, how many adults are away feeding at any given moment, hatching success rates, and the observation methods that would minimize disturbance. What this exercise does it make students identify variables and structure a complex real world situation before a single number appears? That is genuinely mathematical thinking. And it is exactly where modeling starts, not with a formula, but with the question, what do I actually need to know? This movement between the real world context and the mathematical world begins right here in part A. Now, I want to take a moment with this cycle diagram because this is the lens we are going to use to trace exactly what happened in our team's work on part B. Looking at the diagram, you can see the movement from the real world problem context through translating into the mathematical model, then working mathematically to produce mathematical outputs, then interpreting and testing those outputs back against the real world. The cycle is not linear. We moved back and forth between phases throughout our work. Zainab is going to walk you through each of those phases now, starting with translating and structuring.
Thanks, Uma. I'll now focus on the mathematical modeling competencies and how our group's solution maps onto the modeling cycle. The real world question is which colony should receive conservation resources? To work mathematically, we had to translate that into something tractable. How many nests does each site contain? But here's what's interesting, that translation required a definitional decision that shaped everything else. What counts as one unit? An egg, a chick, an active nest. We chose to count nests and treated each visible white shape in the aerial photograph as a proxy for one active nest. This is where the task is genuinely strong, and I want to be specific about why. Using Speak 2025 framework for analyzing modeling tasks, this task calls for substantive assumption making, not just looking up a typical value, but making judgments about features of the context itself. We made three. First, nest density is uniform across each colony site, which the memo supports by confirming habitat is uniform. Second, each visible white shape was treated as one active nest proxy. Third, the shadowed area in colony A was counted conservatively rather than ignored or treated as equal to the rest. None of those were automatic. Each required reasoning grounded in the biological context of the task. That kind of assumption making is rarely foregrounded in school mathematics. This task makes it unavoidable. From those assumptions, we built our procedure step by step. First, we measured the printed scale bar with a ruler and converted the photograph dimensions into real world meters. For both colonies, the sample photograph area came out to about 2,000 square meters. Then we overlaid a hand drawn quadrant grid on each photograph, counted nests independently, compared our tallies, and resolved any differences by recounting together. Next, we calculated nest density as nests per square meter. Colony A was 0.123 nests per square meter, while colony B was 0.371 nests per square meter. We then estimated the total colony area by counting grid squares on the satellite site map. Colony A came to about 4,400 square meters, and colony B came to about 5,300 square meters. Finally, we multiplied density by total area to get our estimates. Colony A had approximately 540 nests, and Colony B had approximately 1,970 nests, which is a ratio of about 3.6 to 1. No formula was provided. We designed the procedure ourselves. That's what the mathematizing phase looks like when the task is genuinely open. Before we wrote our final recommendation, we ran three validation checks. First, we confirmed that the sample area was smaller than the total colony area for both sites. It's a basic plausibility check, but an important one. If the sample had somehow been larger than the total site, that would immediately signal a measurement error. Second, we went back to the photographs. Colony B appears much more densely packed than colony A, so our ratio of 3.6 to 1 needed to reflect that visual difference, and it did. Third, we compared our density values against published norms of ground nesting colonial water birds. Both fell within ecologically plausible ranges. That loop, moving from the mathematical output back to the real world context to ask whether the answer actually makes sense, is exactly what the interpreting and validating phases of the modeling cycle require. What I find especially useful about this task is that those checks arises naturally. Students are not explicitly told to validate. The task design creates conditions where checking feels necessary. One final note on task design. Part A is more open and creates richer decision making during the structuring phase, while Part B is more scaffolded because the photographs and maps are already provided. In Speaks et al.'s terms, that reduces some decision making in the mathematizing phase, but here that feels like intentional scaffolding rather than a weakness. Adam will now take us through the sustainability dimensions.
Thanks, Zainab. My job here is to look carefully at the sustainability dimensions of this task. And we want to be honest about both where it delivers and where it falls short. So, is this a sustainability task? Yes. The American white pelican recovery from threatened status happened because of deliberate habitat protections decisions informed by population data. Students are using actual methodology behind real conservation choices. That authenticity is important. It's not a simulation. To assess the sustainability potential, we're drawing on the Green Comp framework developed by Bianchi, Pisiotis, and Cabrera. Markle and Kim and Lee apply this framework in their work on sustainability competences with primary students. Green Comp identifies 12 competencies across four areas: embodying sustainability values, embracing complexity, envisioning sustainable futures, and acting on sustainability. The Pelican task has genuine potential to elicit at least three of these. Let's walk through each Green Comp competency this task can elicit. Green Comp 1.3 is promoting nature. The background reading for this task makes a point that's easy to overlook. Walking into a nesting colony causes the birds to leave and the eggs to die. The reason for using aerial photographs is not purely about data accuracy. It's about not harming the animals being studied. Students who engage seriously with that encounter the idea that nature has claims on human behavior, not just nature having uses for us. That's competency 1.3, and it's embedded in the task context. Green Comp 2.1 is systems thinking. The task shows students a chain. Nest count leads to conservation priority, which determines habitat protection, which shapes long-term population recovery. These aren't separate facts, they're interdependent elements of a system. Now, when students see their number connected to a conservation outcome, systems thinking becomes a concrete act rather than an abstract concept. In Green Comp 2.3, it's about problem framing. There's a prioritization problem built into the task. Resources are limited, and the memo states that larger colonies get protection priority. Now, students aren't just calculating, they're engaging in the with the logic of triage under scarcity. Which habitats matter, who decides, and on what basis. That is problem framing, which is a real ethical core. Here's the honest limitation, and we think it matters for teachers in Alberta specifically. This task is framed entirely from the perspective of the US federal institution. Students are positioned as technical helpers to that institution, and there's no engagement with the indigenous relationships to the lands and waterways where these colonies nest. There's no question about who has historically cared for these sites, or whose values should shape what counts as a conservation priority. In Alberta, where many of these waterways are on treaty lands, that silence is significant. Markle in 2026 draws on Pasquale, Balvanera, and Anderson to argue that modeling tasks should engage with diverse values of nature, including relational and intrinsic values, not only the instrumental value of population data for institutional decision making. The Pelican task, as written, operates almost entirely within that instrumental frame. Now, that does not disqualify the task. It means that if you want students to think critically about the priorities that shape conservation decisions, you'll need to build that layer deliberately. A discussion prompt that asks who owns the land and who should be consulted. A paired reading that brings in the Indigenous land stewardship perspective. A question about what data cannot capture. The task will not go there on their own, but it doesn't mean that it can't go there.
So here is what we would say to a colleague thinking about bringing this task into their classroom. The Pelican Colony's task is worth using. The mathematics is substantive, curriculum connected, and genuinely open. Working through it ourselves showed us that the modeling cycle comes alive precisely because of the assumption making and the validation process. Students have to think, not just calculate. The task adapts across grade levels, and the real conversation context gives students a reason to care about getting the numbers right. On sustainability, it opens genuine conversations about species protection, systems thinking, and the ethics of prioritization. But the critical layer, whose world is being modeled and whose values count, needs to be added by the teacher. That is not a reason to avoid the task, it is a reason to go in prepared. Use it, adapt it to your local context, ask the questions it does not ask. Thank you.